But seawater diagenesis is not the only type of diagenesis that can happen in the marine realm. In fact, if you are in arid condition, there is a whole sway of transformation that can also happen. So this diagram here shows what happens chemically to seawater when it is evaporated. So on the horizontal axis, we have the proportion of the original volume remaining. We start with half of the original fluids that remains, and we end with only 1% of the original fluid that remains. Now on the vertical axis, we have density in gram per cubic centimeters. And it starts at 1 and finishes at 1.3. And you can see that when we evaporate seawater, we have a predictable sequence of minerals that will precipitate. We start with low amounts of iron oxide. The thickness of the line shows the amount, so it's low amount of iron oxide. Then we go to calcium carbonate. So we have a cement that precipitates straight from seawater when you evaporate it. So that's a calcium carbonate cement. At first the volume is low, but then it becomes important when you reach about 20% of seawater remaining. Once all the carbonates are precipitated, you go into the sulfate minerals. So that's when you have gypsum being precipitated. And it's only when you go to less than 10% of the original volume of seawater remaining that you start to precipitate the table salt that you're familiar with. So NaCl, halite, precipitates late in the process, and sylvite precipitates even later in that process. Sylvite is KCl, and that's also when you start to see some exotic phase precipitating, so for instance magnesium sulfate. But notice that we are at 2% of seawater remaining, so that's extreme evaporation. But the take-home message here is that through evaporation of seawater, you create a fluid, a new fluid, evaporated seawater, that has very different chemical properties than the original fluid. And a different fluid means different style of diagenesis. And in fact, in evaporative condition, we can have dolomitization. And the way it works, and this is classic for the Middle East, but also for ancient examples in Europe or in America, is that you have fresh water. Fresh water is maybe not the right term, but fresh seawater that comes into a semi-restricted environment. Now, those lagoons can be several hundreds of kilometers wide in the case of the Middle East, so this is not a small feature. And as water circulates into that lagoon, evaporation takes place. That means that this seawater, original seawater, becomes chemically transformed. It becomes actually denser and more enriched in minerals. And because it is denser, when it reaches the end of the lagoon, it will tend to sink to the bottom of the lagoon and then circulate close to the sediment. And in fact, it will enter the sediment. And that is known as seepage outflow. And the whole process can lead to dolomitization or precipitation of dolomite in ancient deposits. So that is known as seepage reflux dolomitization. What's interesting about seepage reflux dolomitization is that where you are on the depositional profile plays a big role. So that's an example here from, again, the Guadalupian deposits of the Permian Basin by Saller and Henderson. And what you see is that where we have the hypersaline lagoon, right here, we tend to have a lot of dolomite that precipitates. So you dolomitize the limestone, that means you transform the limestone into dolomite, plus you fill pore space with the new mineral, with a cement of dolomite. So you lose all the porosity. In the middle here, you tend to have dolomitization of the limestone, but your fluid is no longer able to precipitate a cement, so you no longer have cement precipitation. So you have a porous dolomite where you don't have cement in between the grains of dolomite. And finally, if you're too far from the evaporative lagoon, nothing happens because you don't circulate the fluid, so you end up with a non-porous limestone.